doping in semiconductors and drying of clothes. And at this point, you may be thinking, what does doping in semiconductors have to do with drying of clothes, right? On one side is drying of clothes, on the other extreme is doping. How could they be related together? So what I'm going to do is, using this drying of clothes, I'll use it as a metaphor or an analogy to illuminate what happens really in doping. All right? All of you know that analogies and metaphors are very important for learning. And let's see, I'm presenting before you, let's see whether the analogy of drying of clothes can help us understand the doping in semiconductors. All right, so let's go forward and see whether that makes sense or not. Okay, so to begin with, all of you are familiar with this. We draw this model of a silicon lattice showing how silicon atom is bonded to the neighboring atoms. We talk about that if we take one silicon atom substituted by a group 5 element, phosphorus or arsenic, and how that particular atom here has an extra electron, and that extra electron you would read, I'll show you how typically books talk about it, that extra electron is very loosely bound and very easily goes to the conduction band and is available for conduction, right? So that's the view. Let me show you how books talk about it. This is a book that you are all familiar with. Very popular, old book, but very popular book by Millman and Grable. If you read about it, I'll read it for you if it's not very clear. What they're saying is, again, by whether you look at a boron atom or an arsenic atom, the dopant, what they're saying is, we have previously indicated that only a small amount of energy is needed to ionize the impurity atoms. So what they're saying is, the electron, the extra electron which is there, is very loosely bound. And very little energy is needed to ionize the impurity atoms. And the temperature at which electronic devices normally operate, greater than 200 Kelvin, provides sufficient thermal energy to ionize virtually all the impurities. So what they're saying is, even at 200 K, I have enough energy to ionize all the dopant atoms. And 300 K, everything is ionized. All right? Later on in the book, as you go forward, what you read is they talk about, well, when you add an impurity, it introduces a level, a dopant level inside the energy gap. And the electrons, the dopant ionization energy they talk about is, if you look at it, they say a typical value in silicon is 0.05 electron volt, 50 milli-electron volt, right? Now, at this stage, most of us don't bother. We keep on reading and we don't bother. We don't connect these two things here. 50 milli-electron volt is the ionization energy. That's what they're saying. And that's true, 50 milli-electron volt is the ionization energy. What they're saying is, even at 200 K, I have enough energy to ionize. Now let me ask you, at room temperature, at 300 K, what is the average energy of an electron? KT, right? We talk about KT, which is 26 milli-electron volt. So at this stage, you should question, how is it that I have enough energy to, I don't have 50, an average electron does not have 50 milli-electron volt. It doesn't have 50 milli-electron volt at 300 K. And how are they saying that I have enough energy to ionize all the donor atoms? Why am I not connecting the two? 50 milli-electron volt here, and how much energy an average electron has. So how are they ionizing? An average electron does not have 50 milli-electron volt. Well, that's one book. Let me talk about others. This is one of the most famous books, Streetman, right? This is taken from Streetman, and Streetman is, you can read Streetman, all of you might have done that. Let me quote from there. What he says is, this level is filled with electrons at 0 K, and very little thermal energy is required to excite these electrons to the conduction band. Same thing, very little energy. And Banerjee and Streetman, they go on to say that at about 50 to 100 K, virtually all of the electrons in the impurity levels are donated to the conduction band. At 50 to 100K. 100K, if at 300K an electron has 26 milli electron volt, at 100K it will have 1/3. Average electron energy goes as kT, right? With temperature. So at 300K it will have 8.6 milli electron volt. Right? How much energy is needed to ionize the donor atoms? 50 milli electron volt. Average energy is 8.6 milli electron volt. What are they talking about? How are they saying that 8.6 milli electron volt is enough to ionize when the gap, when the donor energy is located 50 milli electron volt below it? How are they saying all this? Why is nobody questioning? Why aren't you guys questioning? Questioning this. 8.6 milli electron volt and 50 milli electron volt is the ionization energy. How is it getting ionized? Right? Okay. Let me take, this is one of Yogesh's mentor, Chen Ming Hu. You will hear more about him. I'm just showing this thing, Chen Ming Hu. Same thing, he calculates and all that, and he effectively says, note that he says 50 milli electron volt. All of them say ionization energy is 50 milli electron volt, and they say enough energy is available to ionize. Right? 50 milli electron volt, and donors have, and they call it very small ionization energy. 50 milli electron volt is very small ionization energy, but I'm saying, all of you may agree, kT is only 26 milli electron volt. So how is it small? It's small relative to band gap and other things, that's fine. But it's not small to the thermal energy that is available. That's only 26 milli electron volt. How are they saying all this? Right, so all of you know this picture that when I add a donor, or you can read about it, when I add a donor atom, the extra electron can be modeled in terms of an hydrogen atom. I'll not go into all of that. And you can calculate the donor ionization energy. So this picture that we have here, that when you add a donor, the donor impurity atom introduces a level here, which is located below the conduction band. And using a sort of a modified hydrogen atom picture, we can calculate what the ionization energy is. So I'll not go into that. More textbooks I can show you. This is a book again by, these authors are from IBM Research Center. Look at what they say. In most cases, the thermal energy at room temperature is sufficient to ionize the impurity atoms. They're all saying that. I have enough energy at room temperature to ionize the atoms here. They're all saying it, right? But they're not. I mean, if you take a look at it, it doesn't appear to be making sense. I don't have enough thermal energy. It's not making sense. But they're not explaining it. How does ionization occur there? Nobody is asking, well, if the thermal energy is so less compared to the ionization energy, how is ionization really occurring? That they're not explaining. I'm not disputing that they are not ionized. We know that they're ionized. But how is it occurring when not enough thermal energy is there? Right? So my issue is ionization of donors so obvious? We take it as obvious. We read the books, and we've been, all of us, I also study semiconductor devices. I also read, well, it's very small ionization energy. I also accepted it. Thermal energy is 26 milli electron volt. I accepted it. I never connected the two. I never asked the question, how is it, how are they getting ionized, right? So, as I said, if you take a typical donor, arsenic, the donor energy is 54 milli electron volt. Phosphorus is 44. And typically, arsenic, phosphorus are the typical ones. So let me take 54 milli electron volt, all right, as the donor energy. Now, at this stage, whether things are ionized or not, so you recall that what they're saying is that the thermal energy is enough to ionize. The electrons would love, it seems as if the electrons would love to go to the conduction band. There's so much energy available, ionization energy so less, what is being implied? The electrons would love to go to the conduction band. Well, do they really love to go to the conduction band? How do we tell? Well, you just heard maybe in the introduction that you use Fermi-Dirac distribution function, probability. Probability of finding an electron in EC versus probability of finding an electron in ED, right? Well, so let's take that Fermi distribution 1 by 1 plus exponent E minus EF by KT. That gives us a probability of finding an electron here. Let me approximate it by neglect the 1, do the Boltzmann approximation. And then what I can calculate is, what is the probability of occupying this level versus the probability of occupying this level, right? Let's compare the two probabilities. I can take the ratio. You take the ratio FED by FEC. Just put some numbers. KT is 26 millielectron volt, arsenic 54 millielectron volt. What you find is probability of occupying the donor level is 8 times higher than probability of occupying the conduction band. Probability of occupying the donors is 8 times higher than probability of occupying the conduction band. So electrons don't love to go to the conduction band. Why would they love to go to the conduction band? The probability of occupation of donor level is much higher, 8 times. If you do that calculation, remember somebody was saying even at 100K, right? If I do that calculation at 100K, the probability of occupying the donor level is 500 times higher. The electrons would love to stay in the donor level, right? They won't love to go to the conduction band. Probability is 500 times higher, right? So the issue that I'm raising is, so why are almost all the donors ionized? I'm not disputing that. I'm not saying the textbooks are wrong, that the donors are not ionized. I'm not disputing that. But I'm raising the issue why. The thermal energy is not enough. So why are they all ionized? All right? So in that context, and further, let me increase your curiosity. Let's take two semiconductors. The curious case of two semiconductors. I often sometimes present this to the students. I say, well, we have two semiconductors, A and B. Semiconductor A, the donor energy is located 6 millielectron volt below the conduction band. Semiconductor B, the donor energy is located 40 millielectron volts below the conduction band. Then I ask the question, let's say I dope both of them to 10 to the power 17 donor atoms. In which case will ionization of donor atoms be higher? In case A and in case B, in which case more donors will be ionized. And the students obviously say, why are you even asking? One is 6 millielectron volt, the other is 40 millielectron volt. It's not a question, right? We are not dumb, it's not a question. Isn't the obvious answer is semiconductor A? The donors are located 6 millielectron volt below the conduction band, the electrons, and the other case is 40 millielectron volt. Where is the question? Right? Where is the question? We'll come back. Okay? All right, so this is the dilemma that I'm posing before you. So how does drying of clothes give us insight into doping in semiconductors? So we all know about boiling of liquid. Liquid molecules, we know, enter the vapor state when they have sufficient kinetic energy to overcome the intermolecular forces. We know that if I take any liquid water molecules are attracted to each other, they are hydrogen bonds. If you want a water molecule to go into the vapor state, it has to have enough energy, right? Right now, I think you can see the analogy that I'm building. Water molecule going from the liquid state to the vapor state is somewhat similar. Evaporation, vaporization is similar to electrons going from the donor level to the conduction band. Ionization is similar to evaporation. That's the analogy that I'm building, okay? So you know that when does an average water molecule have enough energy to go into the vapor state? The boiling point, right? When you have a boiling point temperature, water, if you take 100 degrees Celsius, an average molecule may have enough energy to go into the vapor state, and very quickly, all the water molecules are in the vapor state, right? That's the boiling point. Okay. But nevertheless, clothes do dry at temperatures less than 100 degrees Celsius, right? You take out and put out clothes, the outside temperature is 30 degrees Celsius, the clothes do dry. Average molecule may not have enough energy. We said average molecule may have enough energy at 100 degrees Celsius, the boiling point, right? At 30 degrees Celsius, an average molecule may not have enough energy to go into the vapor state. But clothes do dry. They do dry at 30 degrees, right? They'll dry at 25 degrees also, okay? 100% vaporization you get. Clothes get perfectly dry, right? You bring it back after a few hours, all the clothes are dry, okay? So what am I saying? I'm saying that this is sort of illustrating to you that, look, an average water molecule may not have enough kinetic energy to go into the vapor state. Average, I'm saying, may not have, but the clothes do dry. Here also, an average electron may not have enough energy to go into the conduction band, but just like you get 100% vaporization here, you do get 100% ionization here. Right? I'm building an analogy here, vaporization versus ionization. You do get 100% ionization, or close to 100%, right? Just like here. But can this analogy, I'll not go into too much details of this, can this analogy further tell something about doping? Well, all of you know the drying of clothes depends on what, besides the fact that there's temperature? Yeah, humidity, right? All of you know this. Drying of clothes gets difficult when humidity is high, right? When humidity is high. What does high humidity really mean? You know that the air outside is sort of saturated with water. So the water in my clothes doesn't have enough space to go into. The air already has too much water in it, so it can't go here. Same thing happens here. Ionization is not just about, unlike, when you start reading the textbook, ionization is not just about donor energy and temperature. It's about, crucially depends on the number of states in the conduction band. Humidity is telling you it's not about water, it's not about temperature only, but it's about the surrounding, the atmosphere. It's about that also, humidity. This is also. Ionization is not just about where the donor energy is and what the temperature is, but crucially depends on how many states are there in the conduction band. It crucially depends on that. And that is one of the most important factors, which I'm not saying the books don't talk about it, but they talk about it in an implicit manner. They will have somewhere equations and all that in which you will find that the conduction band density of states and all that will come into picture. When they're describing doping and they're describing ionization, they're not talking about the crucial role of the density of states in the conduction band. Very important. So, by the way, if you're thinking that evaporation of water may be very simple to understand, this is a paper some of you may want to read. 2015 paper, Physical Review Letters, one of the very prestigious journals in the field of physics. 2015, you have somebody writing a paper, Molecular Mechanism of Water Evaporation. How does water really evaporate? What really happens here? So when you look at the molecular picture and the details of it, how does a water molecule acquire enough energy to go into the vapor state and all that, these things are more involved. You can, if some of you have interest, you can read this later on here. So coming back, what we are saying is, it's not that the electron here in the donor has, an average electron has a lot of energy to go into the conduction band. It's not that the electron loves to go to the conduction band. The electron, as we said, the probability of occupying the donor level is 8 times higher than the probability of occupying the conduction band. But what we should ask is not just probability. We should ask how many electrons are there in the conduction band and how many electrons are there in the donor level. So what we have to do is, if we take this ratio, number of electrons in ED and number of electrons in EC. So the number of electrons in ED would be total number of states, which is ND multiplied by the probability. And the total number of electrons in the conduction band would be total number of states in the conduction band multiplied by FEC. Now, once you do that, then you find this, if you take 10 to the power 16 here, you find this ratio is 2.8 into 10 power minus 3. That the number of electrons in ED is almost 1,000 times less than the number of electrons in EC. Even though the probability, the electrons would love to occupy the donor states. But the number of electrons that actually exist in the donor state would be probability multiplied by total number of states. Similarly, number of electrons that would be there in the conduction band would be probability multiplied by total number of states. So the reason why donors are getting ionized is not because they love to go there, but one of the main reasons is there are too many states available. A lot of states available here, EC. A lot of states available, that's why they're going there. Even though the probability may be low, lower than probability that it occupies ED, they are getting ionized because there are a lot more states. So that's the accurate picture. Unfortunately, what most textbooks and all that are talking about, they're ignoring that aspect. They're not explicitly talking about it. What really leads to ionization? It's not that the energy is very small compared to the average amount of thermal energy. It's not that. It's because the number of states are so much larger. Okay? They're not emphasizing that particular point. And so what happens is many students carry this impression. They keep on telling, sir, there's very little energy required. And that's why they're getting ionized. They're missing this very important part here. Okay, so donor ionization, if I go into the details, I'll not go into the equations. What we can do is we can calculate this. We can calculate that what is the minimum temperature required for ionization and things like that. So, for example, this expression you can get. This expression tells you what is the temperature at which you get 90% ionization. What is the temperature at which you get 90% ionization? So T is 300, EC minus ED by 26, ln NC by ND. So if you look at, that's what I'm saying, the most textbooks and all that, when they're qualitatively talking about doping, they're talking about this factor, that EC minus ED versus 26. And they're saying that factor is, sort of they're implying, is very small. It's not small. EC minus ED by 26 is a factor of 2. EC minus ED is 54, divided by 26 is almost 2, right? And this is 300 Kelvin, right? So if I just look at this, most donors will be ionized at 300 into 2, 600 Kelvin. But the reason why they're getting ionized at lower temperature is this factor here, ln NC by ND. So along with EC minus ED, thermal energy, all of that, the important factor is NC by ND. How many density of states do I have, and what is the level of doping that we have? And this ratio, NC by ND, is this ratio which brings this factor T to 126K here. That the number of states is so much higher compared to the number of donor atoms. All right, so we can derive this particular equation also. We can take this equation here, we can rewrite another equation. Another equation tells us is that how much doping can I add and still get 90% ionization, right? So it tells you that how much this gives you that number of dopants that you can add and still get 90% ionization. So let me come back to this curious case of two semiconductors, right? As I said, in one case you have 6 millielectron volt, in the other case you have 40 millielectron volt. And I'm asking the question, in which case will I get more ionization? And both are being doped to 10 per 17. At this stage, with this background, you should say, we cannot answer this question. Because besides the ionization energy, besides the temperature, what else is important? Density of states. So at this stage, you should say, well, give me the density of states, then only I can answer. What is the density of states here, and what is the density of states here? Without that, you cannot understand ionization. It's an incomplete picture. Just the energy and temperature are incomplete. What is the level of humidity? That's important to tell how fast will my clothes dry or whether they will dry or not. That humidity is this. What is the density of states, right? So at this stage, if I tell you that my semiconductor A has a density of states 4 into 10 per 17, and my semiconductor B has a density of states which is 2 orders higher, 4 into 10 per 19. Let's consider these two cases. Now, will all my donors be ionized here? Well, this is the equation that tells me. This equation tells me how much donor can I add and still get 90% ionization. So if I calculate this factor on the right-hand side, this factor comes out to be 1.6 into 10 per 16 for case A. For case A, it turns out to be that you can add only 1.6 into 10 per 16 and get 100% ionization. If you add more than that number of donor atoms, you will not get 100% ionization. Now, what are we talking about? We are saying we are adding 10 to the power 17. So will I get 90% ionization? The answer is no. I'm adding above 10 to the power 17 is more than this limit here. So less than 90% will be ionized in case A. I'll calculate the same factor for case B. For case B, what do I find? 4.3 into 10 power 17. In this case, what will I find? 90% will be ionized. So here is two cases, semiconductor A and B. In one case, you have 6 millielectron volt. In the other case, you have 40 millielectron volt. 90% of the donors are ionized in case B, and less than 90% are ionized in case A. Now, are these hypothetical examples? The answer is no. The numbers that I've given you is sort of typical of this is gallium arsenide. If you add a donor atom into gallium arsenide, you'll get typically 6 millielectron volt. And this is somewhat similar to silicon. Silicon is 40, 50 millielectron volt, is like that. Gallium arsenide has very low density of states. 4 into 10 power 17 is a typical number for gallium arsenide. For silicon, it's about 2.8 into 10 power 19. Just for the sake of simplicity, I've taken 4 times 10 power 19. So case B is like for silicon. Case A is like gallium arsenide. 6 millielectron volt is now, this is literally 6 millielectron volt is much smaller than average thermal energy. Average thermal energy is 26 millielectron volt, right? In case A, you should say, yes, they should all be ionized. And in case A, they are not ionized. While in case B, you'll say 40 millielectron volt is larger than average electron energy. And here, everything is ionized. Why? So what is being said is that ionization is not just about the energy, temperature, but it's also about the density of states. Very, very important how many states are there, right? So it's very important there. So as I said, I mean, the most textbooks, the flaw that I find in most of the coverage of doping is, take this book, Donald Neiman, they're all very similar. They all say, if a small amount of energy is added to the donor, it can go into the conduction band. I have a problem with that. If a small, 50 millielectron volt is not small. Average energy is 26 millielectron volt. So, but they are making that statement. Further, the same textbook will say, here they are saying small amount of energy is required. Then in the next page, they will say the energy is 45 millielectron volt, 50 millielectron volt. How is it small compared to thermal, right? Then they will, in the next further page, they will calculate what is the ionization probability. And when they're calculating ionization probability, they have factors like this. So what is very important is that they're harping on this, EC minus ED by KT. What is the, how many donors will be unionized will depend on, yes, EC minus ED by KT is an important factor. How much is the ionization energy, how much is the temperature is an important factor. But the crucial factor, one of the most important factors is this, NC, number of states. That they are not explicitly talking about it. I'm not saying that it's not there in the equation, I'm talking about something new. People do understand density of states is there, but they're not talking about it explicitly. They're harping upon ionization energy and temperature and implying as if there's enough energy available to ionize, right? Enough energy is not available. And so finally, as far as ionization is concerned, what I'm saying is you don't need enough. An electron need not have enough average energy to ionize. It will nevertheless ionize. Just like an average molecule may not have enough energy to go into the vapor state, but clothes do dry at temperature less than 100 degrees Celsius. Yeah. And further, the analogy is drying of clothes gets difficult when humidity is high, implying, well, pay attention not just to energy or to temperature, but where these electrons are going. They're going to the conduction band. That's the atmosphere for us. The conduction band is the atmosphere for the electrons. And if the atmosphere is saturated with electrons, if there are too many electrons already, ionization will become difficult, just as drying of clothes gets difficult. Now, before I leave this particular topic, I'll leave you with it. All of you know that drying of clothes becomes easier if there's humidity, if I switch on the fan, right? What does switching off fan imply for doping? Right? I don't want you to answer, but think about what would switching off fan imply for doping? Right? Like a humidity, I'm saying, is related to number of states. Switching off fan causes a drying to become easier or faster. What does switching off fan mean here in doping? What does that analogy? Does it say anything? By the way, remember, all analogies and metaphors will break. Drying of clothes is a different phenomena, and doping is a different phenomena. At some point, the analogies will break. So if you stretch it too far, it will break. But in a limited sphere, they may help you to understand something which is, doping is an unfamiliar topic. Drying of clothes is a very familiar topic, right? So it will help you understand how this is really happening here.